right, so keep in mind there's two things when we talk about fatty acids. So fatty acids have to be synthesized versus oxidized. So oxidized is the breakdown of fatty acids, and we call it oxidized because oxidized is when you're removing those electrons. So we're focused here on the breakdown. So when we start with the breakdown of fatty acids, we have to start with lipolysis. So lipolysis. Lysis always means the breakdown. And we're basically going to take this, I tend to start with palmitate. Palmitate is a 16 carbon fatty acid. And so what's going to happen is this guy is going to be in your adipocytes. So here's going to be an adipocyte. Okay, can't spell. Adipocyte. And this is going to be on triglycerides. So here's a triglyceride. It's got 3 fatty acids, and here's the glycerol group. And so we got to take off these fatty acids from this glycerol. And to do this, we have to activate lipase. So remember, lipases are what's going to attack this guy and take off the fatty acids. And the specific lipase that's going to do this is hormone-sensitive lipase. Hormone-sensitive lipase, or HSL. And what turns hormone-sensitive lipase on? Glucagon or insulin? Glucagon. We're in the fasted state. You only break down stuff when you're in the fasted state. So glucagon is going to turn this guy on, and this guy is going to take off these fatty acids. So now you have this 16 carbon fatty acid that's been removed, and it's going to be put into the blood. So that, again, is the first part. That's the main part of lipolysis, the breakdown of lipids. We got to break down this triglyceride and put these fatty acids. This fatty acid is just typically a 16 carbons fatty acid. This is palmitate. It's the most common one that's used. But now we have the 16 carbon palmitate in the blood, and it's going to go, for example, to your muscle cells because your muscle might want to break down that fatty acid. So this 16 carbon palmitate, so this fatty acid is going to be brought into the cell, and it's going to have to be activated. So a coenzyme A, what's the vitamin that makes coenzyme A? Pantothenic acid. I don't remember if it's B. I think it might be B5. But pantothenic acid, that's a scientific, that's what you should really remember. You should remember B5 too. Those aren't bad to remember. But I want to focus you guys on the scientific language here. But pantothenic acid is coenzyme A, and this CoA has to be added in order to activate this fatty acid. These cells will not recognize the fatty acid unless a CoA is added to it. All right, so now we have it in the muscle cell, and it wants to be, where does beta oxidation occur? In the mitochondria. So we actually are going to have to bring this guy into the mitochondria. And remember, the mitochondria has 2 membranes it's going to have to get through. The first membrane and then the second membrane. And we have 2 transport mechanisms for this, CAT1 and CAT2. So here's going to be, and the C stands for carnitine. Carnitine. Oh, I got to stand up straight again. Carnitine acyl transferase. 1. Oh no, I'm running out of batteries. Transferase 1. And so that is going to take this fatty acid and it's going to bring it in and attach this fatty acid to carnitine. So that CoA is going to come off and the carnitine is going to come on. And then the other one's going to be CAT2, which is going to be in this inner membrane here. So I'm just going to write CAT2. And that's going to bring this fatty acid carnitine into the matrix of this mitochondria. So now it's brought into this inside, and it's going to be converted back to a fatty acid CoA. So FA-CoA, and that carnitine is going to be taken off and put back out in order to retrieve more fatty acids. So, yes, Cat1 gets it into the inner mitochondria of the outer membrane or the outside part of the mitochondria, and then Cat2 brings it into the matrix, which is where beta oxidation takes place. But Cat1 and Cat2, that C stands for carnitine. You cannot transfer long-chain fatty acids without carnitine. Long-chain fatty acids need carnitine for that transport. So carnitine is required. If it's a medium chain or a short chain, and it can actually go into the mitochondria without carnitine, but long-chain fatty acids require carnitine. That's really bad smelling. Require carnitine to bring it into the cell, into the mitochondria, sorry. Can go in, they can diffuse through. All right, so now let's talk about beta oxidation. So beta oxidation is now going to occur now that we're inside of the mitochondria. Beta oxidation can occur, and there's 4 steps. 1, 2, 3, 4. Dadgummit. Oh yeah, I got this. The first enzyme that's really important is acyl-CoA dehydrogenase. And then this first step, we're going to actually break down this fatty acid. So we're going to be taking off 2 carbons at a time. And those 2 carbons at a time are going to become acetyl-CoA. So, and that's what's going to happen in step 4. In step 4, we're going to make that acetyl-CoA. So step 1 is acyl-CoA dehydrogenase, and we make an FADH2. This is an oxidation step. Remember, oxidation, we're moving electrons. We're essentially taking electrons from that fatty acid chain, and we're giving them to FAD. So FAD becomes FADH2. So we make an FADH2 in this very first step of beta oxidation. The next step is, it's a hydration. It's like a hydrolase. I forget the name of the enzyme. Not much happens except we hydrate this guy. We add water. The third step is also important because it's another oxidation. And this one, I forget the enzyme. It's ennoyl-CoA dehydrogenase, I think is the name. Ennoyl-CoA dehydrogenase. I think it's acyl-CoA. It's acyl-CoA dehydrogenase. But this guy is going to make it NADH. So essentially, we're going to be taking NAD+, moving electrons to that NAD+, and making an NADH. So that's why step 3 is important, because in these oxidation steps, it's always a dehydrogenase that does it, dehydrogenase. And we're going to make, in the first step, an FADH2, in the third step, an NADH. And the fourth step is really important. This enzyme is called a thiolase. It's called a ketoacyl thiolase is the full name. I'm just going to write thiolase. But this thiolase is the enzyme that pulls off those 2 carbons and makes that first acetyl-CoA. And then the next parts are just repeat. And you repeat this over and over until you've broken down this 16 carbon fatty acid into 8 acetyl-CoAs. No, it's just the most common one used. Palmitate or palmitoyl-CoA. If it was an 18 carbon, I forget what an 18 carbon is called, then we're going to make 9 acetyl-CoAs. If we're dealing with a 20 carbon or even an 8 carbon fatty acid, 8 carbon fatty acid, we're only going to make 4 acetyl-CoAs. So this is always an odd number of carbons. So if you have a 16 carbon fatty acid, you can make 8 acetyl-CoAs. But what if you have a 17 carbon fatty acid? With odd chain fatty acid, even chain, you just make what we just talked about. But if you're using an odd chain, and there's also something on saturated versus unsaturated, but if you're using an odd chain fatty acid, the end product is actually going to be propionyl-CoA. So So instead of acetyl-CoA, you're going to make propionyl-CoA. This is a 3-carbon. It's not a waste product because this can be converted into succinyl-CoA, which can be put into the Krebs cycle. Enzyme. Is that what you asked? What does that? Oh, all right. So she's going to our vitamin lecture. Vitamin B12 is important for breaking down these 3 carbons. Actually, vitamin B12, cobalamin. Without cobalamin, you get a buildup of these 3 carbons, and that's going to cause neurological issues, which is the toxicity, or sorry, not toxicity, but deficiency of B12 means you're going to have a buildup of this guy, which causes neurological issues, dementia-like symptoms. Yeah. So you need vitamin B12 for this pathway to turn propionyl-CoA into succinyl-CoA. Thanks. Yeah. And I don't know what's on your exam. So saturated versus unsaturated. When you already have an unsaturated, you basically skip this first step. Will I add that to the exam? Probably not. I mean, now you know it. With unsaturated, you don't get this first step, so you won't make an FADH2. That's the only thing. And so all you will make, wherever there's an unsaturated or a double bond between the carbons, you won't get an FADH2. But that's a detail. I don't know if I'll put that. But well, now we talked about it. But
I was gonna say that I think it's important to point out that like as far as the exam questions, we gotta know that like you gotta mix FADH in step 1 and ADH in step 3 and acetyl-CoA in step 4.
yeah, the final product. And you should know, especially this first enzyme, acyl-CoA dehydrogenase. And this is the one where you actually have a family of 4. So the long chain acyl-CoA dehydrogenases will break down long chain fatty acids. Short chain acyl-CoA dehydrogenase will break down the short chain. But yeah, the first step actually is 4 different enzymes depending on the size of the fatty acid chain. But yeah, that's really it. Like the first one's an important one. You make an FADH2. The third one is another dehydrogenase, but that is where you make an NADH. So total, the final products of beta oxidation, each round of beta oxidation is going to make 1 FADH2, 1 NADH, and 1 what? Acetyl-CoA. Or propionyl-CoA if it's an odd chain. But this is mainly what we make. So each round of beta oxidation will make 1 FADH2, my handwriting, I've only got 2% left, 1 NADH and 1 acetyl-CoA. Did that help kind of down? Do you have a question, Joseph?
Yeah, what does the word say?
You can't read that? Enoyl, E-N-O-Y-L, acyl, A-C-Y-L, CoA, and the DH stands for dehydrogenase. That's the name of the enzyme that makes the NADH. Yeah, enoyl, acyl, CoA, dehydrogenase. It's this really annoyingly long enzyme name. And it's important just because it makes that NADH. The thiolase at the end is really important because that's the one that makes the acetyl-CoA. I'd say the first, and yeah. I know this is like from a million weeks ago, but you guys got this. Do you guys want to talk about fatty acid synthesis while we're here? While we're here, let's do fatty acid synthesis. So this is going to be the opposite. So this is this going to happen in the fed or the fasted state? You're not going to make, if you're already in, so I guess it kind of, like in the fasted state, you're not going to be building new fatty acids. You're going to be breaking them down. But when you're in the fed state, fatty acid synthesis, for example, you're going to be able to take all that glucose you just ate, if you just ate a donut, and you're going to be able to convert that into fat. So that's why this is going to happen in the fed state. So insulin is going to help stimulate this guy. That's when you're going to be making extra fat, storing it on your bodies when you're in the fed state. So fatty acid synthesis. So fatty acid synthesis it always starts, so whenever you make a fatty acid, you're always, or any lipid, not any lipid, but generally speaking, cholesterol, ketones, fatty acids, you're starting with acetyl-CoA. That's the starting material. All right, so step one. Oh, darn it, what is the enzyme? Acyl-CoA carboxylase. I care because I am a good coach.
Hey, yeah. Hey.
I care about your degree even if you don't. All right, this acyl-CoA carboxylase, remember carboxylase, we're going to carboxylate acetyl-CoA. So acetyl-CoA is going to come in, and remember acetyl-CoA is a 2-carbon. So we're going to add a carboxyl group to this, and we're going to make a 3-carbon mevalonate or malonyl-CoA. 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 Cholesterol is mevalonate. And so this is the first step. We got to make this malonyl-CoA because that's going to be important for the next part. Darn. Oh well, I guess.
It's stupid. You have MSP.
How do I? Let me just flip this up a second. I gotta finish it now. I've gotta started it. You can't just. All right. So we have first step was where we take acetyl-CoA and we add a carbon to it. So any carbon, I'm using bicarbonate, and we're going to make malonyl-CoA. And this malonyl-CoA, this is really important for the next step, which is going to be the second enzyme. So the enzyme that does this is an acyl-CoA carboxylase. Carboxylase. We're adding a carbon. We're going from a 2-carbon acetyl-CoA to a 3-carbon malonyl-CoA. The next step is FAS. F stands for fatty. Fatty acid synthase. And this guy does the rest. Essentially, this guy already has, and I didn't talk about how this happened, but it already is going to have an acetyl-CoA added to it, because there is going to be a step where that happened, and we didn't really talk about it much. But just assume there's a 2-carbon acetyl-CoA already attached. So every time we add something to this fatty acid synthase, and we're going to be adding malonyl-CoAs. So malonyl-CoA is going to come in, and remember, it is a 3-carbon. So you add a 3-carbon malonyl-CoA, and you end up with a 5-carbon. So this fatty acid synthase is going to have a 5-carbon. It would have had a 5-carbon, but what's really going to happen is 1 carbon is going to leave. It's carbon dioxide. And so we end up with a 4-carbon here. So now we have a 4-carbon fatty acid. What's going to happen is this, I'm going to get it right here. So we have a fatty acid synthase, now with the 4-carbon attached. Another malonyl-CoA is going to come in. And again, malonyl-CoA is a 3-carbon. So we're going to end up with 7-carbon, but again, another carbon dioxide is going to be lost. So this 4-carbon is going to be converted into a 6-carbon. Fatty acid synthase, 2 carbons added, you end up with a 6-carbon. And you're going to keep doing this over and over. Fatty acid synthase is just going to keep adding malonyl-CoAs and removing a carbon each time, and you're going to grow this. So if you want to build a 16-carbon fatty acid, then you have to do this 7 times. Because 2 plus 2 plus 2 plus 2 plus 2 plus 2, every time you're adding 2 carbons at a time, because one of the carbons from this malonyl-CoA is going to be removed. And you're just gonna keep doing this to grow whatever chain length you need. So really, there's just two major steps with this. I mean, there's a lot of other details. If you go back to my slides, you'll see the big picture from the textbook. But it's really two major enzymes. And this one, fatty acid synthase, is actually a complex of enzymes. Is this going to require ATP? Yeah, you're going to need ATP for this. But again, the first step is making malonyl-CoA. The second step is using this fatty acid synthase and taking all of those malonyl-CoAs and adding them to grow the fatty acid chain. That's like a snapshot of fatty acid synthesis. But acetyl-CoA is a really important component. We got to start with that, convert it into malonyl-CoA, and then we go with malonyl-CoA the rest of the time. That's what fatty acid synthase is going to use. Yeah.
So on the bottom of it, you also think about that as
6 carbons.
yeah. You also think about that as just like acetyl-CoA plus malonyl-CoA. Well, no, it's really not like carbon.
But yeah, each time a malonyl-CoA is added, you lose a carbon. So these are just, it's just a 6 carbon fatty acid. 1, 2, 3, 4, 5, 6. It's just a 6 carbon fatty acid.
So would it be wrong to think of it as like acetyl-CoAs?
I wouldn't say it's wrong, but that's not like how I would think of it. I would think of it as a 6 carbon fatty acid, not CoA, acetyl-CoAs. It's not acetyl-CoA. Acetyl-CoA is a 2 carbon. But I mean, but if that works in your brain to help you remember and
Like if I took out 2 of those carbons on the end, that would be acetyl-CoA.
no, you would have a 4 carbon.
No, the 2 carbon that's not.
Oh, the 2 carbons that came off, yeah, then that would be acetyl-CoA, and that's what happens in beta oxidation. So fatty acid synthesis is adding 2 carbons at a time. Beta oxidation is removing 2 carbons at a time, and when you do that, they're removed as acetyl-CoA. So I see where you're going with that. There was a question back here.
Fatty acids malonyl-CoAs or
The first step is acetyl-CoA is converted into malonyl-CoA, and then fatty acid synthesis only uses malonyl-CoA. So the second step only uses the malonyl-CoA.
Why does the acetyl-CoA?
Because that was the first step. The first step is all of this. That's the first step to make malonyl-CoA, and this is the second step. Oh, I see what you're saying. This acetyl-CoA is already added to the fatty acid synthesis, so it already starts with an acetyl-CoA. There's another reaction that happened prior to this with fatty acid synthesis. So this acetyl-CoA was added to the beginning. It was just a different reaction. So just assume fatty acid synthesis already comes with an acetyl-CoA attached. Because it does. And there's part of the fatty acid synthase that does that. We just, it is in the slides. I talk about it, but. Right. So that's fatty acid synthesis and fatty acid breakdown, which is called beta oxidation. Kind of a snapshot, yeah. Unsaturated fat has the double bonds, and that's what makes it, gives it a kink and makes it liquid at room temperature. As saturated fats do not have double bonds, they do not have kinks, so those fatty acids sit on top of each other and become solid at room temperature. I don't like that question. Which one's healthier? Because I would say it depends. If you look at the research, unsaturated is healthier. But I don't like that question because I think it depends.
The one that's not healthy is trans fat.
Yeah, I would definitely say trans fats need to be removed. And that should definitely be something on your board. So, and even saturated fats being less healthy than unsaturated might be on your board. So, unsaturated fats, generally speaking, fats that come from plants tend to be healthier overall. They do tend to lower risk of heart disease.
Confirmation bias. Getting out of the floor.
Is it vegan?
Are you not vegan?
I used to be for a long time, and but ultimately when I moved back to Georgia, I'm like free for all, whatever. Anything that's made with love, I will eat it. or donuts, whether they're made with love or not. Krispy Kreme all the way, but you know, donut's a donut. But Krispy Kreme, they're so fluffy melting them out. So that'll be on the exam. We got 20 minutes. We want to jump through some more hoops. I actually prefer this whole board thing. I do wish I had a bigger board though.
This is cool. I was gonna say that that's just not the right amount of carbon. I mean, I know it's not like important, but it's just like 1, 2, 3, 4, 5, 6.
Six. Okay.
Because yeah. I mean, it's not important.
It's so important.
It is.
What else did we start? Oh, we started out with lipid digestion. That's what lipid structures, lipid digestion, and then we talked about fatty acid synthesis and fatty acid breakdown. HMG-CoA. Where do you see that? And what synthesis of what? Cholesterol and synthesis of what other thing? Ketones. So ketones, remember, ketones are a product of acetyl-CoA. So when you have a lot of acetyl-CoAs accumulate, you start making ketones out of them. And so one of the first products of making ketones is HMG-CoA. Because you take 3 molecules of acetyl-CoA, you put them together, you make HMG-CoA. Hydroxy, butyryl, methyl, whatever. I always forget the name of HMG-CoA. Hydroxy, methyl, glutamyl, no, whatever. But yeah, HMG-CoA is also seen in ketone synthesis, which is regulated by what? What turns on ketone synthesis? Insulin or glucagon? Glucagon, because it's fasted. You only make ketones when you're in the fasted state. And so if you're on a ketogenic diet, you tend to be fasted. You tend to not eat carbohydrates. So when you're on a really low carbohydrate diet or when you're fasted, that's when you make ketones. So starvation, that will accelerate the production of ketones. And ketones are acidic, so it can lead to ketoacidosis if it's dangerous, especially if you have diabetes. But yeah, ketones are in the fasted state. Yeah.
So those would be the only two reasons why there would be ketones in someone's urine.
Yeah, too much ketones or a ketogenic diet you'll see ketones in the diet, but in the urine. But typically, you shouldn't see ketones in the urine unless something like that is going on.
What about like a situation?
I don't know. I don't know about children, but typically you shouldn't. So if you're burning a lot of fat, that's what it starts accumulating ketones, and you typically don't start doing that unless you're in the fasted state. So I wouldn't say that you seeing ketones in the urine is definitely a sign that something is bad. Urine is interesting because it's just part of the story and such an isolated part of the story. You really need like more information to find out if, like, even protein in the urine is not necessarily a bad thing. Generally speaking, it can be very bad. It could be a sign of kidney failure. But protein in the urine could also be you just ran 6 miles, and that could put protein in the urine transiently, temporarily. So, yeah, sorry, urinalysis is not going to be on your exam.
What if you wrote as well?
I don't know about that one. It comes from a lot of fatty acid oxidation. When you break down a lot of fatty acids, you make a lot of acetyl-CoAs, which can lead to ketone synthesis. And the growth means that you might be, children would be more metabolic because they're growing, and that means they might be using more fatty acids. But I don't know that much about children urinalysis. I've only really looked at adults. Yeah. Acetone is what is it? Like, it's one of the ketones. Is it the one that is metabolically active? Can we make ATP from it or acetyl-CoA from it? No. It's the one that we breathe out, or it kind of has this fruity smell to it, but it's not metabolized. It's just it's one of the ketones that's made when we convert HMG-CoA. So HMG-CoA is made first, and then when we convert HMG-CoA, so what are the 3 ketone bodies? We have acetone, No, that's actually not a ketone body. So when you have, so acetyl-CoAs come together, and you make HMG-CoA. HMG-CoA, you just need 3 acetyl-CoAs and you can make HMG-CoA. And then HMG-CoA can be further broken down into acetone, but also acetoacetate. And so these are the ketone bodies, and the other one is just really loud. What's the third ketone body? Yeah, my brain's just it's not hard, or I guess it is the harder one to remember. It's hydroxybutyrate. Hydroxybutyrate. And there's so this is the third one, and this one is the one that's not metabolized, but these other 2 can actually be converted back into acetyl-CoA. And if you can do that, you can make ATP out of them. But this one, acetone is just breathed out. So it's just a side product. Acetone is. It's still considered a ketone body. So acetone, acetoacetate, and 3-hydroxybutyrate. No, both of these can be converted to acetyl-CoA. If there is, there might have been something that one is more easily converted to acetyl-CoA than the other one, but both of them can be. Acetoacetate makes hydroxybutyrate. So this is, and when you do this, you actually make another acetone. So there's that component, but you don't have to remember that kind of detail. And ketogenesis. And ketogenesis, even though you're building something, it's still in the fasted state. So this is glucagon is going to stimulate ketogenesis because it's what happens in the fasted state. Yeah.
Fun fact, when I did my 74-hour fast, my breath smelled like fruit because of the acetone.
Yeah. That really does. Yeah, there's things like that. If you can personalize it, it makes it easier to remember these things. Like I remember when I was first learning this, I really wanted to know how to live forever, and I thought biochemistry was really important in that. So I was able to connect to this information, I think, a little more easily than some of you who are like, you just want to start doing the stuff that you came here for, not learning the scientific language. Maybe there could be like a side component of chiropractors that's just adjusters, and you don't learn the chemistry part, you just learn the adjustment. And
They do exist, they're just not doctors.
so is there a program for them, or did they have to operate in the shadows?
They definitely is, I don't think so.
Okay, in the United States, you probably have to have, just like I used to be a registered dietitian, I could work in hospital settings or a lot of other places as a nutritionist. But there's a lot of nutritionists out there that actually probably have a lot of good knowledge, but they aren't allowed to work in hospitals or they aren't certified. But I guess that's the.
And then there is certified ones
that just regurgitate the crap that I learned as a registered dietitian, like drink milk for calcium and blah, blah, blah. Yeah. They just regurgitate what they learned. They don't think about it.
Yeah.
So that could be anything. Like you could be there's plenty of physicians that have no clue what they're talking about when they prescribe these pharmaceuticals. They have no clue. So it is it's whatever you want to make of it. And I don't care, honestly, ultimately in the end, what you choose to do. If you just become an amazing chiropractor and can't remember what this stuff is or care, it doesn't matter to me except that you got to pass the board. I would love it if you could grasp this too and add this component to your capabilities, but I'm not trying to hammer this in your head except for the fact that you got to know this for the next year at least for the boards, whenever you have to take that exam. So, guys can, and I don't if I see you guys in a year, whenever you start studying for this, it's gonna be a lot harder for me to help you if you didn't want to